So up to this point, we've been dealing with, I'd say, we can split them up into, let's say, three different properties of an object, right? We've got one object in space, whatever, on planet Earth. Where is it, right? What's its position? What is its motion, right? Is it moving, and is its motion changing, right? Does it have a velocity? Is that velocity constant, right? So where is it? How fast is it going? And how massive is it, right? When we talked about chapter 4, we introduced the idea of mass and how it's related to force. So we've got position, motion, and mass, right? And so we've defined all of these terms surrounding those properties of an object and how they change. So chapter 6 is just another concept based upon these properties. And so Isaac Newton originally, I think he referred to this property as an object's motion. Right? Today, velocity is how we describe an object's motion. But Isaac Newton referred to motion as what we now call momentum. Right? So not just an object's velocity, but how massive it is. So we define momentum as an object's mass times its velocity. Right? We use a lowercase p for momentum. Momentum is a vector quantity because mass is a scalar, velocity is a vector. Right? So if I have a velocity, I have a momentum in some direction. Right? So we can see by this equation that if I'm stationary, right, if I'm stationary and my velocity is 0, my momentum will be 0. If my velocity is changing with respect to time, right, let's say that's a delta v over delta t, right, my momentum would be changing. So a little exercise here I was thinking about, I usually do this in class. Make this v a delta v over delta t. Right? Make this a delta v over delta t. And so this would have to be delta p over delta t. Alright? But delta v over delta t is a. Right? So this would be acceleration. This would be my change in momentum with respect to time. The right side would be ma, which is net force. So that's actually the original version of Isaac Newton's second law. We call it F equals ma. It's actually net force is the change in momentum with respect to time. Alright, so just an interesting thing. We'll actually see the product of that derivation on the next slide. But just an interesting thing to see that Newton's second law was actually introduced in terms of an object's change in momentum. So momentum has units of kilograms, meters per second. Right? And we don't have anybody special that we named this unit after, so it's just grouped like this, right? Kilogram, meters, seconds. That's how we, those are the units of momentum. So, speaking of a momentum's change, how do we change an object's momentum? In this course, we're not going to change an object's mass. Right? An object's mass will remain constant with respect to time. How do we change an object's momentum? We have to change its velocity. We have to change its velocity. So how do I change an object's velocity? And if an object's velocity is changing, it's got to be accelerating. In order to accelerate an object, we have to apply a force. Now, we can't apply a force instantaneously. We have to apply it over some time interval. Okay? So apply a force over some time interval. We're generating what's called an impulse on the object. I'll use a capital I. Some textbooks use like a capital J. I'm going to use a capital I. Force is a vector, so that means impulse is also a vector. Right? Vector times a scalar is a vector. So this is algebraically how we would calculate the impulse acting on an object. So a force isn't always constant. If you remember back in chapter 5, we could take the area under a force position graph and calculate the work done. We can do the same thing here for impulse. You see this is force times time. Work was force times displacement. We have a force over a time interval that will generate a force time graph, and we can take the area under that curve and calculate the impulse. So we can do it algebraically or graphically like we did with work. So this, we'd have to use calculus, right? This is an algebra-based course. So all of our force time graphs will be linear in nature, so we'll be able to use geometry to calculate the impulse. All right, so I have an impulse, right, which is a force over a time interval. We did that little Newton's second law exercise up here. We generate a force, we change an object's velocity, we change its momentum. Okay, so this is the impulse momentum theorem. Any object experiencing an impulse is experiencing a force over a time interval, so it's accelerating, its velocity is changing, its momentum is changing. So that means the units of momentum, right, this is momentum, the units are also Newton's seconds, right, Newton's seconds. So we can describe momentum in units of kilogram meters per second or Newton seconds, because Newton seconds is a kilogram meter per second squared times seconds, right, and one of those goes away. Okay, so these are two different ways we can express the units of momentum. And I'm going to use this a lot. So this is like a three-part equation, right? So I'm gonna use each of these terms. I can set them equal to each other however I want, and solve for whatever's missing. Take the left side and the right side, set them equal to each other, divide both sides by delta t, and there you'll have Newton's original second law, right? F is delta p over delta t. And for all you calculus fans out there, you know, those deltas for a non-constant force, those deltas become lowercase d's, right? So force is actually the first derivative, the first time derivative of momentum. But again, algebra-based course, I won't ask that, but just interesting. So how does an object's momentum change? It, with the exception of gravity, all of our forces have been contact forces, right? So for an object to accelerate, it's got to experience a force, it's got to come in contact with another object. Okay, so if we have two objects, they are interacting with a collision, or through a collision, they're exerting forces on each other over some time interval. They're actually changing each other's momentum. Okay, so that's how we change an object's momentum, through collisions. We've got two different types of collisions we'll talk about in this section. All right, so it's just an interaction between two objects that come in contact with each other. So we've got two types of collisions. The nomenclature is very similar, so I'll do a couple examples and I'll make sure to identify the type of collision that we're dealing with. We've got two types, inelastic and elastic. All right, the first one is inelastic. Okay, inelastic. In both of these collisions, momentum is conserved. All right, so in an inelastic collision, think about you've got an object sitting on a platform and you throw a piece of clay or a piece of putty at it, right? They'll collide, but they'll combine, right? And then they'll move along as quote-unquote one object, right? So they stick together and then they move along together as one object. The system has kinetic energy initially, right? One object at least has to be moving. But kinetic energy is actually lost, right? It's actually lost during the collision. So kinetic energy is not conserved, but the momentum of this two object system is conserved. Right? So that's an inelastic collision. Two objects come together and then they combine and then they move together as one object. Second type of collision is an elastic collision. An elastic collision, if you think of like two billiard balls, right, or two rocks, or two massive and dense solid objects. If they combine, they're going to hit each other and then bounce off of each other. Right? So they're going to go their separate ways in a new direction, and they're going to stay their own single objects, right? They're not going to combine. So elastic, think of two billiard balls colliding, bouncing off each other, making that like click sound. And then inelastic collisions, two objects that are kind of like sticky, and they come together and they combine as one. All right. So I'm going to solve these very similarly to conservation of energy problems. So I'm going to set the initial state equal to the final state, much like I did in chapter 5. All right. So if I have these two objects, even if they collide, if I isolate them inside my system, the net force on the system is zero. Right? If the net force on the system is zero, there's no impulse generated on the system by any external source. So delta P equals zero, which means the final momentum of the system is equal to the initial momentum of the system. All right, so this is my law of conservation of momentum. If the system is not experiencing a net impulse, which means it's an isolated system experiencing no net force, the total momentum of the system does not change. So there's another conservation law for us. All right. If I go back to the impulse momentum theorem, if I equals 0, delta P equals 0, P final equals P initial. Momentum does not change in an isolated system. And generally we can tell right off whether it's an isolated system or not. Either you'll be asked to find the impulse generated, or you'll be given some impulse. Right? That way you'll know it's not an isolated system. Okay? If you're dealing with a collision and impulse is not mentioned, it's an isolated system where momentum is conserved. Okay? So we're going to deal with our elastic collision, our two billiard balls who are coming in contact with each other, right? Both have a mass, both have a velocity, so that means both have a momentum. My system bubble is going to go around these two objects. I'm going to label my system as an isolated system, no external forces. They're going to apply forces on each other, but those are forces within the system, right? It's a Newton's third law pair. They're changing each other's momentum, right, by applying an impulse on each other, but the total momentum of the system is unchanged, right? So if I found these objects' momentum values and added them together, they'd be the same as they were up here. All right, so that's an elastic collision. So here is an example of an inelastic collision. Okay, it's not like two gobs of putty or anything, but two train cars are going to collide, and then they're going to become attached, and then they're going to move together. So we'll take a simple case where the masses are the same, right? They're of equal mass. In a lot of cases, one object will be stationary, right? Sometimes it'll have a velocity, sometimes it'll be stationary. So this object has no momentum. This object has some momentum, right? It's an mv initial. They're going to combine, and they're going to have a new v final, but they're going to share a v final. In an inelastic collision, the two objects are going to have the same final velocity because they're moving together as one object. So what I did was just kind of a derivation of both of these cases. So we'll talk about slide 8 first. This is what a conservation of momentum equation looks like for an elastic collision. Okay, so slide 8 is over here, right? Object 1 has a momentum, object 2 has a momentum. Notice the subscripts, right? This is object 1 with an initial velocity v initial 1. Object 2, initial velocity v initial 2. They don't stick together, so now they're going to have their own final velocities, right? V final 1, v final 2. Their masses don't change, all right? So this is how we're going to set up all of our elastic collisions. Now, obviously, I've got 1, 2, 3, 4, 5, 6 variables, right? So in reality, I'm going to need at least enough information to deduce the value of 5 of these variables, right, and solve for 1, right? Usually, you know, one object's at rest, maybe one object is at rest after the collision, which helps us like get rid of terms and stuff like that. But we're going to need more information to actually like get a value of something that we're looking for. Slide 9 is our inelastic collision. In this example, both the train cars have the same mass. So m1 is equal to m2. We just call it m throughout the derivation. Now this isn't exclusively for all inelastic collisions, just this train car problem. But this first equation is how we're setting up an inelastic collision, right? Two objects that are separated with their own individual values for momentum, right? mv, mv. But then they combine and have a new mass, which is the sum of their original masses, and then they have a shared final velocity, right? So there's only one momentum term on the right side. Now I'm doing initial equals final. Again, a lot of textbooks say final equals initial. I just like the initial to be on the left, final to be on the right, no big deal. Okay. So in this case, I just substituted m for all the masses, right? Because in this special case, the masses of the train cars are equal. And the second train car is initially at rest, so this whole term goes to 0. So I'm left with mv initial 1 equals the sum of the two masses, which is 2m v final of the two train car system. The m's go away, and we see that the final velocity is half the initial velocity of the first train car, which kind of makes sense, right? One car is going, say, 4 meters per second. They're both the same mass. This one's stationary. They're going to move along with a velocity of 2 meters per second, right? Which physically kind of makes sense, right, in a collision. They're both going to slow down. Kinetic energy is not necessarily conserved in an inelastic collision, but the velocity, the relationship between the velocities kind of makes sense. So I'll briefly touch on a two-dimensional collision, and I'll have an example towards the end. So since momentum is a vector, two-dimensional collisions are still going to follow the law of conservation of momentum, but we have to take our momentum vectors and we have to split them up into their x and their y components. So we're still using this conservation law, right? But we have to write two conservation statements, a conservation statement in the x direction and a conservation statement in the y direction. So that basically consists of taking all of your momentum vectors and then splitting them up into x and y components, and then solving two different conservation of momentum statements. Okay, so I'll do an example of that later in the section. So I've got two examples of an object that's experiencing an impulse, right? It's experiencing an impulse because I'm given a time, duration, and I'm given a magnitude of a force in both of these cases. So in example 9.8, this is the graph. Example 9.9, this is the graph. Right, they're both experiencing forces. It's actually the same object. It's a 2 kilogram object, and it's got a same initial speed. It's got a speed of 1 meter per second. So I'll just say this is positive and it's to the right. Okay, so according to my reference frame, this object is moving to the right. I need to find the object's speed and the direction of the object after it experiences this force, this impulse. Alright, so for 9.8, I've got a force of 2 newtons over a time of 1 second. It's got an initial velocity of 1 meter per second, and it's got a mass of 2 kilograms. Okay, so again, I'm just going to say, I'll zoom out a little bit here. I'm just going to say that the initial velocity is in the positive x direction. So it's got a momentum of 2 kilogram meters per second. And I got its mass, I've got its velocity. The force is positive, so I'm going to say it's going in the same direction as the velocity. Okay, so it's a force of 2 newtons over a time interval of 1 second. So I'm using my impulse momentum theorem. I'm using the delta p, and I'm setting it equal to the f delta t. Because I know the object's initial momentum, the mass doesn't change, so I'm looking for the final velocity that's contained here in my final momentum. Right, so I calculated the initial momentum, I'm given the force and the time interval from the graph. I can solve for P final, and that contains P final. Right. So what I did is I just separated it into MV final minus MV initial. I added MV initial to both sides. Right. So I've got my final momentum term right here. All right. MV final is equal to F delta T plus MV initial. Divide both sides by the mass. I'm solving for V final, right? That's final momentum. I want final velocity. Divide both sides by the mass. Everything's positive, right? The initial velocity is positive. The force is positive. So I plug my values in, and I get a speed of 2 meters per second. Right? It's still positive. right? My initial velocity was positive, my force was positive. So this makes sense. Something's moving in the positive x direction. I give it a force in the positive x direction. It speeds up in that direction. All right. So that's my new velocity. Using the impulse momentum theorem, I calculated the impulse from the graph. I knew the initial momentum because I knew the object's initial mass and velocity. I need the final velocity that comes from the final momentum. Nearly identical process for this example. The difference is the force is now in the opposite direction. Right? It's a negative force. Right? So just like with work, if I had an area under the x-axis, that area was negative. So same thing here. I've got a negative impulse, negative force over a time interval. Still have the same initial velocity, still have the same mass. So I'm using the same process, right? All the algebra is the same. I'm looking for V final. The difference is my force is negative, right? So, and my force is negative and it's sufficiently large enough that it's actually going to change the direction of this object. I've got an initial velocity in the positive x direction, force in the negative x direction. Once I plug my values in, I'm actually getting a new velocity of negative 1 meter per second, but that's in the negative x direction. So the force was applied opposite the object's motion and actually was sufficiently large enough to change the object's direction. Okay? So that's how we calculate impulse from a force time graph. And we use the impulse momentum theorem to find something out about the object later. So we'll do another impulse problem. We've got a 0.2 kilogram softball. It's pitched horizontally at 25 meters per second. So what I'm going to say is, again, my reference frame, I'm going to give the softball a velocity in the positive x direction. We'll say the bat that hits the ball is hitting is applying a force in the negative x direction, right? Softball's coming towards you, you swing the bat in the opposite direction. Okay. So once the bat hits the ball is now moving in the opposite direction at 35 meters per second, right? So I'm going to say that velocity is negative. So I'm given the time interval, 0.8 milliseconds, so make sure we're converting these to seconds, right? 0.8 milliseconds is 0.8 times 10 to the negative 3 seconds, which is 8 times 10 to the negative 4 seconds. All right. So we're given the time interval, we're given the change in velocity, we're given the object's mass, which is constant. So we're asked for two things: the force exerted by the bat and the impulse experienced by the ball. So I is F delta t. I'm actually going to solve for the impulse first. So I'm going to set the impulse equal to the change in momentum, which is P final minus P initial. Write it as mv final minus mv initial. The object's mass doesn't change, so I can factor it out if I want. Substitute 0.2 kilograms in for the mass. V final was negative 35 meters per second minus a positive V initial. All right, so that works out to be negative 60 meters per second. So mass times velocity is, or times change in velocity is negative 12 kilogram meters per second. So that tells me the impulse is in the negative direction, which makes sense with my system. Right, the force is acting in the negative x direction. So I found the impulse first. The reason I found the impulse first was, now that I have this value, I want to set I equal to F delta t. Right? So I want to solve for F, divide both sides by delta t, so F is the impulse divided by the time. I found the impulse. I was given the time interval in the problem. So I'm also getting a negative force, very, very large force, right? But it takes a large amount of force to change the velocity of an object that's moving with that great of a speed. Okay, so you're actually applying a very, very large force on a baseball or a softball when you hit it. Okay, so don't be too concerned when you're getting large forces in this type of situation. So I'm going to do two, excuse me, I'm going to do two inelastic collision type problems, and then I will pause the video, try and keep it under 30-40 minutes wherever I'm at now. So I'll do these two problems, upload it, and then I'll move on with an elastic collision problem. Okay, so 35 gram bullet. So first thing I think to myself when I see grams, I think I'm in physics land. Everything's got to be in kilograms, even if it's not reasonable, right? Even if this is a very small mass. So I got a 35 gram bullet strikes a 5 kilogram stationary piece of wood. The bullet becomes embedded in the wood. So that tells me I'm going to answer part B first. The bullet is embedded in the wood. Both move together at a speed of 8.6 meters per second. All right. So this is an inelastic collision because the two objects come together and then move after the collision as one object. All right. And I'm looking for the initial speed of the bullet. So I'm given the final speed of the system, I'm given the two masses, and I also know that the wood is stationary. The wood is at rest. So I'm going to say M sub B for mass of the bullet. I convert it to kilograms. So 0.35 grams, is that what it was? Or 35 grams. That's 3.5 times 10 to the negative 2 kilograms. Mass of the wood is in kilograms, 5 kilograms. The initial speed of the wood is 0. The wood is at rest. We're looking for the initial speed of the bullet. So B for bullet, W for wood. The final speed of the system, the block wood system, is 8.6 meters per second. So I'm going to say, to make my life easier, everything's moving in the positive x direction. Right? So I expect a velocity of the bullet to be positive. So it's an inelastic collision. They move together. I go back to my inelastic collision momentum conservation setup. Right? Initial momentum of the bullet, initial momentum of the wood, final momentum of the system. This term goes away because the velocity of the wood is 0 before the collision. So that whole term gets to go away. Very nice. So now I'm left with this, and I'm looking for the initial velocity of the bullet. Right? I'm given the final velocity of the system. I know everybody's mass. All I've got to do is divide by the mass of the bullet and get the initial velocity of the bullet by itself. Now I can plug everything in. Right? I've got a very small mass for the bullet, very large mass for the wood. But I'm dividing by a very small mass. So what actually happens is I plug my values in. I get a very, very high speed for the bullet, right? Which does make sense, right? Bullets travel at a very, very high rate of speed. So I'm getting a high velocity for the bullet. So that makes me feel good about my answer. Again, inelastic collision. This is kind of like the train problem because one of the objects is stationary. And again, I'm given all the values of my variables to solve for one. All right, last inelastic collision. This is technically what's referred to, I've seen it referred to as an explosion. Right? It's an explosion. So if you ever see an object being fired from something, right? A gun or a cannon or something like that that shoots an object like a projectile, there's going to be a recoil. Right? So there's not really, it's not like an explosion where a bunch of pieces are flying all over the place. But the system is combined initially. And then something happens, there's a reaction. Right? There's a reaction where the objects go off in different directions. So that's what's happening here. It's kind of the reverse of an inelastic collision. So we've got a 500 kilogram railgun, fires a 2 kilogram DU pellet horizontally with the velocity of 300 meters per second. So that means the pellet has a final velocity of 300 meters per second. The gun and the pellet inside the gun are initially at rest. It's on a frictionless surface, so we'll say the system is isolated, no work, no impulse done on the surface. What's the recoil speed of the cannon? So I'm looking for the speed of the cannon after it fires the railgun. So again, I'm going to treat it as an inelastic collision in reverse. All right. So they're initially stuck together. They're both at rest, and then the gun fires the pellet. The pellet goes in this direction. The gun will go in the opposite direction. So I'm expecting a negative speed or a negative velocity for the gun, right? Because I'm saying that this direction of the pellet is positive. So I set it up like a conservation of momentum problem. It's just that the final momentum is the individual momenta of each object. And then the initial momentum is the momentum of the two objects combined. But the gun and the pellet are at rest, so this whole P initial is actually equal to 0. Right? So there's no initial momentum, which is weird, because how can these objects have momentum if initially they don't? Okay. And what we'll see is one will have a positive momentum, one will have a negative momentum, equal in magnitude, opposite in direction, and so when you add them up together, since momentum is a vector, the total momentum is 0. So we've got the initial momentum of each object individually equals 0. I'm looking for the final velocity of the railgun, so I'm solving for V sub Fg. Again, a lot of subscripts, kind of like we did with like conservation of energy problems, a lot of subscripts, so just take your timing and keep them straight. So subtract the momentum term, the final momentum term of the pellet from both sides. So I get the final momentum of the gun is equal to the negative momentum of the pellet. Kind of like what we were talking about where the total momentum is 0. Right? They're equal in magnitude, they're opposite in direction. Finally, just like the last problem, all I got to do is divide both sides by the mass of the gun. I've got a nice expression for the final velocity of the gun. But it's negative, right? I'm saying the final velocity of the pellet is positive, mass of the pellet is positive, mass of the gun is positive. So I have a negative sign here. I'll get a negative final velocity. So I plug this in, I get a velocity of negative 1.2 meters per second. Makes sense, the gun is much more massive than the pellet, so the pellet's going to have a much higher speed after the firing than the gun is. Right, so you see kind of a proportionality, right? Larger mass, smaller mass. Smaller velocity, larger velocity. Momentum has to be conserved. Okay. All right, so I'm going to pause and I will start up with elastic collisions, an elastic collision example on the next video. All right, thanks.